All right. Volume control, not. All right. Let's come back. We have 45 minutes to wrap up. For the next half of the lecture, I will be talking about the computer system architecture. Well, it's a boring topic for me, since I'm coming from a networking background. But due to the same error Jishank was talking about, I am here today. So, when I say computer system architecture, the first questions come to someone's mind, especially from outside computer science. What are the basic architectures of computer science or of computer systems? If you go to buy a new computer, what are the basic architecture of any computer system that you're going to look at? Well, it looks like Jishank already took all of your energy. So we look at processor, memory, input-output devices, and communication channel that connects all these things. So what do you understand by a computer architecture is that it is actually the specification detailing how a set of softwares and hardware technology standard interact from computer systems or platform. So when I'm talking about operating system, basically the first image comes to my mind is that I have a user interacting with some applications. Those applications taking some calls from the operating systems, and the operating system interact with the hardware itself. So in other words, you guys are dealing with MIPS now. Where is MIPS in the image in my mind? So MIPS basically is a very low level that the hardware can understand. So it's very hard, inefficient to deal with the computer through MIPS all the time. That's why we do have some devices interact with the hardware, like monitor, screen, keyboard, whatever. So what I want to say, we get this inner core level which operate in a very low level, and operating system provide a wrapper around the hardware. Couple of reasons of doing that. It's one, obviously, is that you don't have to deal with the low-level instruction all the time with the computer. It's going to be annoying. You're going to die very soon for it. And the other one is makes the system usable for multiple different pieces of hardware. So you get the operating system that's provide a uniform interface which allow program to get down and do multiple stuff on the same machine. So in terms when I'm talking about operating system, we have a CPU. That's something like MIPS instructions. We have cache memory. We have some larger chunk of memory, like RAM. We have storage devices, and nowadays everything seems to be moved into solid-state devices. And at the very end, we do have some networking channel connecting all these together. So, as I stated before, what the operating system does is to provide an abstraction layer on top of the hardware. Some important characteristics about operating system is running in a user mode, and when you want to do something important may affect the system, then a request is carried out via a system software which is going to make sure that the user's allowed to do such an operation, that it doesn't harm the entire system, and you're doing actually that operation in the right place. So it provides some privileged access to raw machine. It manages the machine resources. And something really important is that the uniform interface which to access the machine level operation, which you already explained. And finally, typically machine have multiple programs executing at once. So if we're going to the past a little bit, some different flavors of operating system. The really old ones is basically the batch. It's like that an operator will load program by hand, showing either plugging in things or in paper type, let's say, to get the program in. The program runs, then load the next one, and keep doing that. So you load one, it runs, then load the next one. So you cannot actually run two at the same time. While nowadays, we have a multiple process running apparently at the same time. Most of the devices in front of you now, you can run multiple programs at the same time. And a cut-down version of operating systems is very famous nowadays. Actually, it's in your pocket. So when you talk about iPhone and Android things, basically with this version, we don't need necessarily to do all the stuff that you do in the multi-user version. And the last thing is the real-time specialized operating system. Think about the stuff that we use, for example, in medical field, when you plug in too many things to a patient. So, it's a bit about history. I hate that. In 1960s, operating systems were handcrafted for particular pieces of hardware. That's really, really stupid. Often handcrafted in assembly language. Lot of work, lots of writing systems, and can only work in a particular hardware machine. And then in 1970s, they decided to write an operating system that is a bit portable, so I can move my program into a different machine and can still run. So the idea made for writing a program which can run in any machine. And later in 1980s, more applications and features made available, like database and important things that we are using in nowadays. So, what is the operating system give you? That's exactly when I'm looking for the abstraction provided by modern operating systems. You have some stuff you allowed to and some stuff you are not allowed to, especially when you are touching the base of the system or harm the device. So we talk about users and access rights, what you can do, what you can't. Providing an abstraction for users, so it provides you with an entity to own stuff, files, processing, and so on. The operating system has to say what you are allowed for. So once you log in, what things you can do and what things you can't. Especially when, take the example when you log into CSE machine. Some stuff you are allowed for, some stuff you are not. SS people can do more things based on their permissions. which you don't have as a student. So, the kernel is a computer program that is the core of the computer's operating system, which complete control over everything in the system. The critical code of kernel is usually loaded into a separate area of memory, which is protected from access by applications programs or other less critical part of operating system, because basically harming these systems will basically end up the life of your device. Hey? By the operating system? So you're talking as a user? Well, that's still based on permissions. So when we say something like what you can access on the operating system's file, is basically the system need to ensure what you can do and what you cannot do, which is in the right place and doesn't harm the device at that point. Well, basically your device can basically go down. Can you play on the, for example, in your own machine, if you want to play on the operating system files, if you delete one of the files, what expect to be happen? Your device will never work. You break the system. When we talk about CSE machine, which you have basically an account to do, if you can play with data that you are not allowed for, what do you expect is going to happen? Well, you can break the system. Exactly. Yeah. So you as a student, you cannot see the stuff that as I can see. So if you have permission to play on these files, or it's actually if you get to play with these files without permission, you are harming the entire system. No worries. So we have privileged mode and non-privileged user mode, which we were just talking about in this short conversation. So an operational state of software that has the highest priority, also called the supervisor mode or supervisor state. It is typically the mode in which the operating system runs, because it has access to all the resources in the computer. So in other words, if I'm talking about instructions are divided into those two categories. Non-privileged instructions is an instruction that any application or user can execute. A privileged instruction, on the other hand, is an instruction that can only be executed in kernel mode. Instructions are divided in this manner because privileged instruction could harm the kernel devices. So when I'm talking about system calls, so what is system calls? Basically, it is a programming way in which a computer program requests a service from the kernel of the operating system. A system call is a way of a program to interact with the operating system. So basically, well, let me show the figure later. So we create processes using, for example, fork, or you can replace your existing process by calling execute. So the idea is we are just calling some function from the system. So the system call is basically an interface that allows control access to all of the models in here which interact directly with the hardware. But that is painful somehow. It's going to be hard to remember or interact with the system all the time over system calls. That's why we do have libraries. So a library, basically, in basic definition, I would say it is a collection of non-violated resources used by computer programs, often for software development. These may include configuration data, documentation, help data, message templates, pre-written code, and subroutines, classes, value types, whatever. So instead of dealing with the hardware yourself by doing the system calls all the time, now we're going to use the libraries, which basically going to create another layer in here. So we deal with the libraries that can interact with the system calls, that interact with the hardware through the system calls. Then we come to the idea of applications. So application, in a sense, it is the program that you are using. The mail system, Microsoft Word, whatever application that you are using. So this is the image that I explained at the beginning of the lecture when I say, when I imagine operating system, the first picture comes to my mind is user interact with applications, then applications interact with the hardware through some system calls. So applications possibly supplied by the system, so like LS, VIM, GCC, all these things, or some implemented by users, like DCC, which assumes used for Python, right? DCC? Yep. So it's written in Python. So when I talk about applications, always applications live in somewhere, like in a path. And applications are generally built using libraries to avoid the headache of using the system calls all the time. So that's create another layer. Now we have applications use libraries that interact with the hardware through system calls. So let's talk about the system calls in a bit of details. So in computing, a system calls is a programming way that a program requests a particular service from the kernel operating system it is executed on. So system calls can be involved directly, and there is a bunch of documentations on the manual section 2. And lots of system calls invoke indirectly from a library function described in section 3 on the manual. So here is an example of different file pointers. You open up a file, you close a file, you scan something from the file, you printf something from the file. So the basic idea when you deal with system calls that you need to deal with the whole bunch of these system calls. But what's going to happen when the system call fails? Basically, if you request something if you request a particular service, and if you make the correct system calls, then the return 0 is mainly the success value of returning, but there is a chance that your system call fails and return the value of -1. So you are putting a request for the system calls to do something. Possibly it cannot do it and may actually fail. Maybe you don't have permission, or some particular resources that is not available on that location at the moment. Lots of reasons can make the system calls actually fails. For example, you do a read system calls. A system call will return how many bytes it read from the file. Let's say you ask to read by X number of bytes, but for some reason it can only read Y number of bytes less than X and return that particular value. So the read function returns the number of bytes it's actually read, but it cannot return any number of bytes for some reason. Then the system call will return -1 in this case. When it just return -1 means it's just immediately stop. You have an error, -1, let's find out what's going on. But whenever it return error, no, the system call message means it still can continue running the program, but for some reason there is a specific error which you can come back later on and find out what is it. Yes? Wael. Yeah. Easy, Wael. Wael.
Wael?
Yep.
Sir? So what is call?
Good question. Well, if I have to repeat myself, I'm not going to give you the exact definition. Let me give you an example. What is a system call? Instead of using a library that is doing something for me, I am going to do it myself. So the system call is the first layer that actually interact with the hardware. So when I have the whole bunch of system calls like read, write, whatever of these system calls. So read, write, open, close, all execute, fork, whatever. All these goes directly to the hardware, which makes it actually inefficient and hard for the user to make the right call every time. That's why we do have the libraries. Now, in most of the languages, we do have a handling exception, except for the C language. So a handling exception, basically, if you request the wrong system call, then the program will transfer you to somewhere else, to different code to resolve that problem or to handle the error. So if I go back to the layers that I explained before, so the user interact with the applications, application use the libraries to make a system calls from the hardware. Yes, so the hardware is actually has the first layer wrapped around it is the system calls. So all these things happen on operating system nowadays to avoid you from talking to the hardware directly over the system calls. Otherwise, you do need an operating system and interact with your device via MIPS, since you are expert in MIPS. I will repeat that later for you, but just let me go quick because we have only 10 minutes left. So, where did we get? All right, so I talk about the exception handling. So some other languages provide exception handling capabilities. So something goes wrong, it transfers the control to another code to deal with it. Let's see. So one of the Linux library function that can actually handle errors is the error handling. So what happened basically in the error handling, whenever your program is running, it faces an error, something wrong, make a wrong system call, the resource is not available, whatever reason, then it runs the error function, which actually return the status of that error, what is it and where is it particularly occurs, and then exit the program and return a message of the error. So that's a failed system call example. I would really encourage you to run such an example, and let's see what's going to happen, and we will start up the lectures tomorrow from here. And you guys are free to go now. Thank you so much. If you have any questions, just come over.